So in my previous video, I discussed some of the confusion around the effect of relative humidity and the airborne transmission of SARS-CoV-2. In short, it's a bit of a mess. There's really no clear correlation between humidity and transmission, one way or the other. This has been shown in both animal and epidemiological studies. So in this video, I'm going to walk through some of the reasons why this really isn't that surprising, and so really go through it mechanistically and why we expect, what we see makes a lot of sense. All right, so like any discussion, we really need to start off by defining some terms and really nail down what we're actually talking about. And so when someone claims that the relative humidity affects the airborne transmission of SARS-CoV-2, what are they actually claiming? There are numerous factors that affect airborne viral transmission. Shown here is a brief summary. All of these are important to varying degrees. Many of these factors are affected by humidity. So, if someone is making the claim that humidity affects transmission, they are essentially saying that the sum total effect of humidity on all of these various parameters results either in an increase or a decrease in transmission. If all of these parameters affect transmission in the same way, the net effect would be dramatic and clear. In this case, increasing humidity increases the likelihood of transmission. Now, things begin to get complicated when some of the parameters affect transmission in a different way than the others. On what side does the balance sit? What is the net effect? Well, that would depend on how important each parameter is. If they are all equal, then having a couple different may be insignificant. But what if one of the parameters dominates? Well, then things can change a lot. For example, what if humid air causes the virus to decay 1,000 times faster? Then it doesn't really matter how these other factors affect transmission. The decay rate dominates. So the question then becomes, how does humidity affect each one of these individual parameters? Are there any that dominate? So to figure this out, you have to actually measure each one of these parameters independently. I cannot stress this enough. It is literally impossible to understand, for example, airborne viral decay solely based on the transmission data. They're connected, one affects the other, but you cannot infer airborne viral decay based solely on transmission data. You have to measure airborne viral decay. So generally speaking, when people talk about humidity affecting airborne transmission, they're generally talking about three things. First is the aerosol sedimentation rates. So this is the degree to which the humidity causes the aerosol to increase size and the particle fall out of the air. Second is airborne viral decay. So humidity basically affecting how long the virus itself survives in the air. And finally, third is the immunity. So essentially the body's ability to protect itself being affected by relative humidity. So with that, let's just walk through these big three and just see what's the net effect of humidity on each one of these different processes. All right. How exactly does humidity affect how long a virus can remain suspended in the air? Well, it's important to understand that humidity doesn't actually affect the virus directly. Rather, humidity affects the respiratory aerosol that carries the virus. This fundamental distinction is often overlooked. So then, the question then becomes, how does humidity affect respiratory aerosol? Well, this means that we are interested in the hygroscopicity of the aerosol. This is one of those weird science terms that simply means how much water does a chemical pull out of the air. When it comes to aerosol science, it's represented by a graph such as this. This is called a hygroscopic growth curve, and it describes how an aerosol changes size by picking up water at different relative humidities. The way you read this graph is as follows. Let's say you have a wad of respiratory fluid. Now, take away all of the water, which leaves you just a mixture of salts, proteins, sugars, and surfactants. If you were to make a 1 micron aerosol droplet of this mixture, and then suspend it in air at 50% humidity, the diameter of this aerosol would be 1.1 microns. If you were to raise the humidity to 90%, the aerosol droplet would be 1.5 microns. And if you raise the humidity again to 95%, it would be 1.9 microns. Now, the utility of this curve is that this ratio is constant, meaning if you took a 2 micron aerosol droplet of water-free respiratory goo an identical relationship would be seen. So at 95%, the aerosol droplet would be 3.8 microns. At 90%, it would be 3 microns. And at 50%, it would be 2.2 microns. All right, so the hygroscopic growth curve is really a useful tool that we can use to predict how respiratory aerosol changes size in different conditions. So then, how do we use this curve to estimate how long exhaled aerosol containing SARS-CoV-2 remains suspended in the air? To answer that, we first need to know the initial size of the exhaled aerosol. Now, during the pandemic, it was found early on that the majority of transmission came from asymptomatic people, meaning it was spread primarily through breathing and talking and not coughing or sneezing. Now, the aerosol produced through breathing and talking has a size distribution like this. Note that this is the size distribution at a relative humidity of 40%. So for the most part, all of the aerosol is under 4 microns. From the hygroscopic growth curve, we can then estimate that the largest dry size of the aerosol exhaled through talking and singing is about 3.8 microns, which is 4 microns at 40% our humidity. And when the humidity is increased to 70%, the aerosol would grow to about 4.6 microns, and at 90%, it would grow up to 5.7 microns. Based on the aerosol size and mass, we can estimate how long they remain suspended in the air. Now, this is an oversimplification in that this model prediction things like airflows generated by people moving are not considered, meaning that all of these values are going to be higher when people are present. No matter, we can use this as a baseline. From the estimate, we can see that the humidity has a moderate effect on how long the aerosol remains suspended in the air. Even in the most humid of conditions, the largest aerosol exhaled from talking will remain in the air for tens of minutes. And generally, most indoor air ranges between 40 and 70%, meaning that the shift in time the aerosol remains suspended in the air due to changes in humidity is mere minutes. And again, the values here are the largest exhaled aerosol from talking in perfectly still air. All of these values are going to go up dramatically for smaller aerosol, meaning that the humidity will only have a tangible effect on how long a fraction of the exhaled aerosol remains suspended in the air. So in short, due to their small size, the aerosol produced through talking and breathing are going to remain suspended in the air for prolonged periods of time, irregardless of humidity. Even more so when you have people, the receivers and generator of this aerosol, are moving around creating drafts. So physically, we expect humidity to have a minor, if any, effect. The question then becomes, well, biologically, how does humidity affect how fast the virus itself loses infectivity in the air? Mechanistically, how viruses lose infectivity in the air is an area of study that I've published numerous articles in. It's a very complex process and worthy of its own videos in the future. In order to understand how humidity affects transmission through altering viral decay, we don't need to know how or why the virus decays, but rather we simply need to know the degree to which humidity affects the overall decay rate. Shown here is how the SARS-CoV-2 Delta variant decays over time at high humidity. For about 15 seconds, the virus remains 100% infectious, then begins to decay rapidly. After a few minutes, the decay rate seems to slow. After 40 minutes, about 97% of the viral infectivity is lost. When the humidity is lowered to 40%, over a prolonged period, the decay dynamic is very similar. However, when you look at a very short time period, the decay profiles are actually quite different. In dry air, about half the viral load is no longer infectious within seconds. The remaining infectious viral load decays at a slower rate. Interestingly, the overall decay at both humidities is similar after a few minutes. So in terms of airborne loss of infectivity, the total effective humidity is only for a few minutes. While the difference in viral infectivity decay rates may affect the risk of transmission, the magnitude is limited due to the short time period when there is a difference. The degree to which this matters is going to be dependent on factors such as distance and time. In a general sense, the effect that humidity has on viral decay is kind of the opposite that has on sedimentation rates. So for example, at high humidity, the virus lives slightly longer in the air, but also falls out of the air slightly faster. And for both of these processes, the effect is fairly small or short-lived. And so when combined, What this means is that humidity has kind of a minor effect on the time in which infectious virus remains suspended in the air, both physically and biologically. So let's go a step further and see how does humidity affect the body's ability itself to protect itself from being infected. The first line of defense that the body has from an airborne pathogen is the mucus lining that covers the airway surface. This layer provides protection in various ways. For example, it acts as a physical barrier that stops the virus from reaching the cell surface. This is part of the body's mucosal immune system. There are some studies that have found that the humidity affects how well this system works. Specifically, dry air is thought to reduce mucociliary clearance. This would make the body less effective at physically removing the virus from the airways. Now, the humidity in the airways below the vocal cords will be above 99.5%, regardless of outdoor humidity, meaning the effective humidity on mucosal immunity would only be in the upper airways. The size of an aerosol affects where it is deposited in the respiratory system. Generally speaking, larger aerosols are deposited in the upper airways, while smaller aerosols penetrate deeper into the lungs. Shown here is a model prediction of where aerosol is deposited in the airways as a function of its size. Now, the way you read this graph is as follows. Let's say you have 100 1-micron aerosol particles. A few of them would be deposited in the trachea bronchial region, so the main airways. About 10 would be deposited in the alveolar region, so the deep lung. About 38 would be deposited into the upper airways, so the head, nose, and throat. Now, this leaves a full 50% of the aerosol that would be inhaled and then just exhaled. Literally half the aerosol at this size simply would not be deposited. Note that these curves will be dependent on ambient humidity and type of aerosol. That said, the general trends shown here are consistent across almost all aerosol types. Importantly, you can use this figure to see where aerosol of any size would be expected to be deposited in the airways. For example, a significant proportion of aerosol that is inhaled will not deposit in the lungs and simply be exhaled. The fraction is indicated by the green shaded region. The red shaded region indicates the fraction that would be deposited in the area of the lungs that would be affected by ambient humidity. The blue shaded area represents the fraction that would be deposited in the deeper lungs and thus would be unaffected by ambient humidity. Now, remember the size distribution of exhaled aerosol from talking and breathing. They are all under 4 microns, meaning that a significant fraction of exhaled aerosol would be deposited in the airways that are unaffected by ambient humidity. So much like viral decay and aerosol sedimentation, the overall effect of humidity on mucosal immunity affects only a fraction of the total airborne viral load. All right, so let's bring this all together. In other words, let's see how all of these processes affect transmission in short distances as well as long. Simple question. What would happen if we were to just increase humidity? This would improve mucosal immunity and thus limit transmission. Moreover, this effect will be independent of distance and time. Now, if you're in the exhalation plume of an infected person, there simply isn't enough time for the virus to decay or the aerosol to settle to the ground, meaning humidity doesn't have enough time to have any effect on these two factors. Now, if you're just outside of the exhalation plume of an infected person, there's still not enough time for sedimentation to have an effect. There is, however, enough time for dry air to cut the infectious viral load in half. Finally, over longer distances, the effective humidity on viral decay will be insignificant. However, the effective humidity on sedimentation will be largest over longer distance and greater time. Okay, so what do we do with this? Well, if you remember at the start of the pandemic, there was discussion around the Swiss cheese approach. In short, what this meant is we can reduce transmission risk through a combination of approaches. We can use what I've talked about here today in a similar way. Now, for example, wearing a mask will increase the humidity in the upper airways, meaning that lowering the humidity in the room won't affect mucosal immunity if you're wearing a mask. So in terms of viral decay, the virus decays faster in dry air, thus this would help in the mid-range. And lastly, dry air will cause a minor, if any, change in long-range transmission due to changes in aerosol sedimentation. So in total, the total effect of a combination of masks and lowering humidity would be expected to be positive. Now, by understanding the individual components of transmission and how they interconnect, we can come up with novel and more effective mitigation strategies. All right, so humidity has a minor effect on the various processes involved in SARS-CoV-2 transmission. And of these effects, they're all kind of counter to each other. So I guess the question becomes, what do you do with this information? And so if the aim is to limit transmission through the air of SARS-CoV-2, what this tells us is that humidity is really not going to be that useful for that. There are far more effective mitigation strategies out there. So things like ventilation, masking, immunization, these processes have been shown to be very beneficial. Humidity is not really going to be one of those. So with that, I hope you found this interesting. I hope it cleared up some confusion. If not, and you have any questions, by all means put them in the comment section below, or ask me on Twitter or Blue Sky. And with that, Mix has all the references I used to make the video, and yeah, take her easy.